We will talk about a magnetic moment, and there are two ways to define magnetic moment. One is using the view of poles, that's in the CGS EMU system, and the other one is using currents in the SI system. And when we have a magnetic moment inside the magnetic field, it feels a torque. So we will talk about this torque acting on a magnetic moment. So we define the magnetic moment vector as a vector that points from the south pole to the north pole. So it's a vector that points from pole strength minus p to plus p. So define the magnetic moment vector pointing from minus p, that is south pole, to plus p, pole strength, north pole, and with magnitude m is equal to p times l. So where L is the distance between the poles. So you can see I have a pole couple here, plus P minus P, and the total distance between them is L. So the magnetic moment here is P times L. It's a vector that points from minus P to plus P. So this is the magnetic moment vector. Okay, so in this configuration, when you have a magnetic field that is pointing in the upward direction, we see that there is a force acting on these couple of poles. The magnetic point always points from a north pole configuration to a south pole configuration. So the minus p is like a south pole and plus p is like a north pole. So we can see that the minus p, the south pole, will be attracted towards the external north pole. So this is the force it feels, and the force it feels is equal to p times h, pointing downward. And similarly, this plus p will feel a force that is pointing upward towards the external south pole, where the magnetic field is pointing towards. So it will be attracted to that, so it feels a force upward as well. So we should note that the force on each pole will be F is equal to P times H. And so let's clarify here that we're talking about the picture in terms of poles that is using CGS EMU units. So that's the picture. Okay, so because I have this force couple acting on these poles, there will be a torque that is being applied to this configuration. As you can see, it is going to rotate until the north pole aligns, the north and south pole, or the magnetic moment vector that points from the south to the north pole, will align with the external magnetic field. So so we see that there is going to be a rotation in this direction, in the counterclockwise direction, until the magnetic moment vector will align with the external magnetic field. So we can write the moment or torque acting on the magnet this will be equal to, for the left hand side we have, with respect to the center here, torque is equal to R cross F, the cross product between the radial vector, position vector of the point of application of the force, and the force F. So you can see that in this configuration, the perpendicular distance between the point of application of the force and the center will be here. So that's the perpendicular distance, R perpendicular. How much is that distance? So since we have this angle theta that appears also on this side, it will be equal to L over theta sine theta. So the torque we will get will have pH, that is the force, multiplied with L over 2 sine theta. And then we will have, for the other one, the same thing, pH L over 2 sine theta. And which way is this torque pointing? So if I define as the z-axis that's coming out, so you can see from the right hand rule, if you curl your fingers in the direction of the change in the angle, you see that your thumb points in plus k hat direction. So we can see that this is basically PHL sine theta in k hat direction. So we find that this is nothing but the torque is equal to cross product of magnetic moment with the magnetic field H. Now, in CGS EMU units, we're going to call the unit of M measured in electromagnetic units, EMU, and P is measured in unit pole strength, whatever that is, and then we have L measured in centimeters, in units of centimeters. So we find that 1 EMU is 1 unit pole strength times 1 centimeter. So you can see that 1 unit pole strength can be called as EMU per centimeter. So it's the same thing as EMU per centimeter. I will have a review of this conversion of units in the next video, but so far that's basically what I have to use for the definition of units in the CGS EMU system. In SI system, so I can put a remark here. In SI system, P measured in ampere meter. So we need a conversion from EMU per centimeter to ampere per meter. Okay, so when you see a magnet that has a north pole and a south pole, so we can call this north pole, this is the south pole. The vector that points from one end to the other end, from the south pole to the north pole, is the magnetic moment vector, M. Okay, and M is measured in electromagnetic units. Now we can look at the same thing in terms of currents. So let's change the picture to SI and look at it in terms of currents. In this case, we have a current loop. A current carrying wire feels a force inside a magnetic field, so that's what you have to recall. So here I have a one-turn coil. It's a square with one side is given by L. It carries a current I. So you can see that this current is coming out of the board on one end, going diagonally towards the other end, and then going into the board on the other end. So that's a current loop. It's a one-turn coil. And if you place it inside the magnetic field, it's going to feel a force. The force F felt by a current carrying wire inside the magnetic field is mu 0 I L cross with H, or it's given as I L cross B. And this will be the force that will be felt on each side of the current loop. And where does this equation come from? Well, this comes from Lorentz law, basically. You have the force on a charge inside the magnetic field is Q V cross with B, or Q mu 0 V cross with H in SI units. And if you look at this, so this is Q dl dt cross with B. So if you have a current carrying wire, then you can see that this will be for a given length L, where you have dq dt L cross with B, so that will be IL cross with B. So that's what it becomes. So this comes from Lorentz law. Basically, it's the same thing as Lorentz law. Okay, so if I look at this dot cross product force acting on each side, I can see that for the current coming out on one side, if your four fingers point in the direction out of the board, in the direction the current is coming, and you curl your fingers in the direction of the tip of your fingers in the direction of the magnetic field, your thumb points to the left. So on one side the force is to the left, on the other side the force is to the right. So you can see that the force couple is trying to rotate the coil until it becomes its normal becomes parallel to the magnetic field. And we can see that the force that we're applying to this will cause a moment. So let's talk about the moment acting on the coil. On the other sides, the forces will cancel, so it's just the one that has the current coming out and going into the board that has a contribution. You can find the perpendicular distance between the force and the point of application of the force. So that is this perpendicular distance. It is going to be since this angle will be theta, this angle will be theta. So L over 2 sine theta. So this is the perpendicular distance r over 2. That will be equal to L over 2 sine theta. So we will have the total moment acting on it, F sine theta L over 2 plus F sine theta L over 2, which will be equal to F sine theta L. And the force is mu 0 ILH, because we have the L vector and the H vector basically are perpendicular to each other. L vector, remember, is defined in the direction of the current. So mu 0 ILH, that is the force sine theta times L, which will be equal to mu 0 IL squared H sine theta. So this will be equal to mu 0 times current times area H sine theta. So we can write this torque, then the torque becomes mu 0 m cross h, where m is defined as a vector that points in the normal direction, in the area vector direction, where the magnetic dipole, a magnetic moment, m is defined as current times the area, points in the direction of the field produced by the coil. Produced by the coil at the center. So we have a new definition of magnetic moment. Magnetic moment vector is now going to point in this direction. So it will be parallel to the normal vector n. So that's the magnetic moment vector, and has a magnitude current times the area. So because I is in amps, the area in meters squared, we have m measured in ampere meter squared. So that's the SI unit. And we're going to show later on the relationship between this magnetic moment measured in ampere per meter squared and also measured in EMU. So what is the conversion from ampere meter squared to EMU? We will talk about this in the next video. Now, one last thing here, we also see that there is an energy that is involved in this process. So when you have the magnetic moment vector that is misaligned with the magnetic field, there's an angle between them, then it feels a torque because there is excess energy of the system. So we have the rotation effect of the force, therefore we see a rotational work done by rotating the magnetic moment by an angle theta. So let's recall the rotational work. The work done by rotating the magnetic moment vector, rotating m, by an angle d theta will be equal to the work that we do, which is the torque acting on it multiplied by d theta, that's against the field. Okay, so we can work on this in CGS EMU units. For example, this work will be equal to the magnetic moment m h sine theta d theta. So for the torque we had basically P times L is the magnetic moment, so this is going to be mh sine theta in k hat direction here. So mh sine theta d theta is the work. So this will be equal to m is pole strength times the distance between the two poles, h sine theta d theta. So if we rotate the magnetic moment vector from 90 degrees with respect to the field to an angle theta, and we define the energy at 90 degrees to be 0, then you will see that the work done by rotating from 90 degrees to an angle theta will be mh integral mh sine theta d theta, which is minus mh cosine theta between 90 degrees and theta. So that will be minus mh cosine theta minus minus plus mh cosine 90, which is 0. So we see that the energy stored is minus mh cosine theta, which is minus m dot product with h. So the energy stored in a magnetic moment at an angle theta with respect to the magnetic field is minus m dot h. So it's going to have its minimum value when it is aligned with the magnetic field, and it will have its maximum value when it is anti-parallel to the magnetic field, so that the energy will be plus mh, because the dot product will give us a minus 1. Okay, so in CGS, this is energy measured in ergs in CGS EMU units. And if we do the same for SI picture, we can repeat the same exercise. We will find that the energy will be given by, instead of minus m dot h, minus mu 0 m dot h, and now the energy will be measured in joules. So energy in joules in SI units. So the conversion between joules and ergs is that 1 joule is equal to 10 to the power 7 ergs. So we have this conversion factor between energies. Okay, so when we say magnetic dipole moment, strictly speaking, it is defined in the small length limit. So when you have a bar magnet, you need to talk about a small distance between the north and south pole, and this basically is the strict definition of magnetic dipole moment. And magnetic dipole moment vector here again points from south to north. So this is our magnetic dipole moment. It is defined as the magnetic moment of a bar magnet in the small length limit but finite moment limit. For a current loop, it has to have a small area but finite moment. So you can see the field lines around a magnetic dipole moment in this figure. So here we have this remark. Magnetic dipole moment m is defined as the magnetic moment of a bar magnet in the small length finite moment limit, or for current loop in the SI picture, small area finite moment limit. So it's the same thing. So you can see the magnetic moment, a dipole moment, is considered to be this limit where we have a very small length and just the south and north poles coming together, and we see the moment vector pointing from south to north. And in the case of a current carrying one turn coil, it will be a very small area but still a finite moment configuration. Okay, so we have talked about the magnetic moment. It's defined as a vector that's pointing from a south pole to a north pole, from pole strength minus P to pole strength plus P. In the CGS EMU picture, it is the pole strength P times L. The force on each pole is P times H in CGS EMU. It's mu 0 P times H in SI. So the moment acting on the magnet, the total torque acting on the magnet we see is due to this force which has a rotation effect, R cross F, and that turns out to be, with our new definition of magnetic moment, M cross H. M is measured in EMU, P is measured in unit pole strength, and L is measured in centimeters. So this lets us redefine a unit pole strength as 1 EMU per centimeter. In SI, the pole strength is measured in ampere meter. So this vector points in a bar magnet from south to north. Now, in terms of the current picture, if you have a one-turn coil square with one side L, a current carrying wire inside the magnetic field feels a force, mu 0 I L cross H in SI units, I L cross H in CGS units if you wish, and I L cross B, we can also say it in SI units, and that comes from Lorentz force. It's the same thing as QV cross B. It's just applied to this problem. We have IL cross B. Okay, the moment acting on the coil is due to this force which has a rotation effect around the center of mass, and we see that this torque turns out to be mu 0 M cross H, where the magnetic moment is now defined as the product of the current in the current carrying coil times the area enclosed by the coil, which is L squared in this case, and it's a vector that points in the direction of the field produced by the coil. So if you curl your fingers in the direction of the current, your thumb points normal to the coil, which is the direction of the field produced by this current at the center, and that is where the magnetic moment vector points. It is now measured in amps meter squared in SI. And we see that because of this rotation effect, when you have the magnetic moment at an angle theta with respect to the magnetic field, there is an energy associated with this configuration. If we define the energy to be zero when it is perpendicular to the magnetic field, the energy, the change in the energy is due to the work done by torque in rotating through an angle d theta. Torque d theta is the work done. If I integrate torque d theta from 90 degrees to the angle theta, so that initially the magnetic moment was perpendicular to the field and finally it is at an angle theta with respect to the field, I see that this energy is minus m dot h. So that is measured in ergs in CGS EMU, And in the same thing applies to the SI picture. We have now energy is minus mu 0 m dot h. Energy is in joules, and the conversion is 1 joule is 10 to 7 ergs. Magnetic dipole moment vector m is defined as the magnetic moment vector in the limit of a very small length bar magnet but finite moment, or if you have a current loop, very small area current loop but finite moment.